Hi, today we're going to talk about transformations in the 2D plane. So we're going to be given some kind of region in a plane which is described by two variables, and via some transformation take it to another plane. So what we're looking at here is something in the UV plane. You can tell because we have coordinate pairs u comma v. And the way it looks is, let's say this is the u-axis, this is the v-axis. We're being told that u is always between 0 and 1, and v is always between 0 and 1. So what that means is we go from 0 to 1 on the u-axis, from 0 to 1 on the v-axis, and as long as both of these are satisfied simultaneously, that's the word and implied here, you would end up staying inside this square. And so maybe we'll call this region here, we'll call this region S. And what we're going to do is we're going to take S into a new plane, the xy plane, via a transformation T. And typically these transformations given to you later on, we'll talk about how you might actually pick one for yourself. But the transformation that we're going to use is this: x equals u squared minus v squared, and y equals 2 times u times v. And what this transformation is going to do is it's going to give us some other something over here, some other region here, R. We're not sure yet what that's going to look like. So the goal of this video will be to apply this transformation to the region S and then see what this region R really should look like. Because this picture I've drawn right here, I'm just going to put the words here, this is not good. This is not what really happens. All right, so how would you do that? I think a way to do that is to look at just one side at a time. So let's pick a color here. I'm going to call this side of the region here, I'm going to call this side S1. And what we can say all along S1 is, so if we look at side S1, we can say that U is between 0 and 1, and simultaneously V is equal to 0. Now, if you're in doubt about that, remember this vertical axis is the V axis, and anywhere along this blue line that I'm highlighting right now, V is staying equal to 0. So what we can do then is we can apply these things, these conditions, in conjunction with the transformation T and see what we get with side 1. And so if we would plug this in, we would get x equals u is some number between 0 and 1. V is 0, so we would have u squared minus 0 squared. And simultaneously, we'd have y equals 2 times u times 0. So y is just going to be 0 the whole time. X is going to be u squared. But if u, let's take a look and underline this in red. If u is just numbers between 0 and 1, any number between 0 and 1, when I plug them in here and I square them, I'm going to get back numbers between 0 and 1. You could just square 0, you get 0, square 1, you get 1. So that means that x is going to stay between 0 and 1, while y stays at 0. So what does that mean for us? It means we could start to draw our other region in the xy plane. So I'm going to make a new page here. I'm going to make this the x-axis and the x and y-axis here. And what we've just shown is that our first side, S1, landed on this piece here that goes from 0 to 1 on the x-axis. And so you might want to call this maybe side S1 prime. I'm thinking of prime from geometry when you used to do transformations of shapes. You might call the image prime. Okay, time to look at another side. So let's go back to the original region here. Let's call this side S2. And what can we say about S2? So let's take this to a new page for a minute. Oops, sorry. Let's take this to a new page and we'll copy all this stuff. We'll go work someplace else here and bear with my slowness. There it is. Okay, and how can we describe S2? Well, S2 has the following property. S2, U is equal to 1 the whole time, while V spans between 1 and 0. Right? V is your vertical motion here, and U is always equal to 1. Okay, the transformation T, let's not forget what that does. T, X has the property that X is equal to U squared minus V squared, while Y is equal to 2U V. So that's what we have. So what we're going to do now is try and plug these things in. So if we take U, for example, and we put it in there, then we get back, what do we get? We get X equals 1 squared, which is 1, minus V squared, because V spans between 1 and 0. And then if we take Y, Y is equal to 2 times 1 times V. So that lets us know that Y equals 2V. Okay, so what I'd like to do is get a sense of what this thing is going to look like in the XY plane. I've got this variable V here that I'd like to get rid of. So I'm going to do that. I'm going to take this expression and say that V equals a half of Y, and then plug it into here. If we do that, we'll get this equation. We'll get X equals 1 minus 1 half Y squared, or X equals 1 minus Y squared over 4. So we would expect some kind of domain restriction as we proceed through this, because just like in the previous problem, we had a domain restriction here where we were able to say, for example, that X stayed between 0 and 1, and X stayed between 0 and 1 because U stayed between 0 and 1. So the question is, can we say anything like that here? Well, we have this relationship that X is equal to 1 minus V squared, and we also know that V is between 0 and 1. So if we start plugging those numbers in, for example, we plug 0 in here, then we know that X would come back as 1, right? So in this case, we'd have X as 1. If we plugged, let's use a different color, we plugged 1 in here, then X would come back as 0. And then any number between there squared is going to be a fraction. So you're going to have 1 minus something. You're going to get numbers between 1 and 0. So we can say now that X, this is the final part of the restriction. So we've got this function along with the fact that X is going to stay between 0 and 1. So the question is, what does that look like? Well, you could start to plug in some numbers and see. So if X were 0, for example, then Y would have to be 2. And you can tell that because if you plug 2 on top, 2 squared is 4 over 4, which would be 0. If we let X equal 1, we want X to be 1, then Y would have to be 0. So now you can tell this graph's going to go from the point 1, 0 up to the point 0, 2. So on our picture then, we can make this parabolic arc that'll go up like this. And this here is the point 0, 2. This over here is the point 1, 0. And we'll call this side S2 prime. So what we're starting to see is that this nice square we had, let's just put this thing around it. This nice square that we had, oops, in this 2D world is turning into some kind of curved shaped object. Okay, so we want to look at the next side. So let's go to a new page. Let's paste something here. There it is. The next side we want to consider is side S3. I'll use maybe black for this. So I'll call this side S3. And how can we describe S3? Well, S3 has the property that V is always 1 and U is spanning between 1 and 0. And let's remember the transformation again. X equals U squared minus V squared, and Y equals 2 times U times V. And so if we plug these things in, for example, we get back X equals U squared minus 1. If we plug V equals 1 into the second equation, let's use another color here, plug it in there, then we get Y equals 2 times 1 times V, or well, it's V equals 1, forgive me, so it's Y equals 2 times U times 1, so 2U. And, well, let's get U alone. So we get Y over 2. And then that can go in here. And you get something that looks kind of like the last one. What happens here? You get X equals Y squared over 4 minus 1, right? And then similar reasoning, if we take, for example, if we look at this equation and this equation together, that's letting us know that X is between, we need to be careful here. I guess the way to do it is think about plugging 0 in here. If you plug 0 in here, you get -1. And if you plug 1 in here, you'd get 0. So now you know X stays between -1 and 0. So you've got this sideways parabola on this domain. And it might look bad at first, but then when we go over to our picture here, hey, that's pretty cool. We're going to stay between -1 and 0, and we're going to have this S3 prime, right? So this is pretty nice. So we can see what we had there. We took the equation y equals, well, that's 1 minus, that's the other one. And then we just found, oh, where did I go with it? Oh, there it is. Sorry. There it is right there. So you can see it's y squared over 4 minus 1. So that's this equation. Y, or x equals y squared over 4 minus 1. This one's x equals 1 minus y squared over 4. And you can kind of guess that this last part is going to just be this missing line here. So we have one more picture to consider. Let's do that. So here we are. We want to take, let's see what color we're going to use now. I guess we'll just highlight it like this for the time being. We want to take that side, which I'm going to call S4, and describe that. Well, in that case, we know that U is always 0 and V is staying between 0 and 1. If we apply the transformation, we get X equals U squared minus V squared, and Y equals 2UV. If we plug 0 in here, we get X equals -V squared. We plug 0 in here, we get Y equals 0. This is a good thing because that means we're going to stay on this horizontal part of the axis here, which we're hoping for. It's not to make sense. If we apply this fact here, we know if we take 0 and square it, for example, you would get 0 squared, and we have -0 is 0. And if you plug 1 in there, 1 squared would be 1, but then the negative of that would be -1. So now you know that -1 is less than or equal to x is less than or equal to 0. And that gives you the final side of your transformed region. So this is side S4. We can call it S4 prime. So you sort of traverse around like this. You're moving around a region. And remember this thing, this is what happens when you take this object we had, our square, and it, after the transformation was applied, ended up looking like this, almost like an arrowhead of some sort, something like that, where these are two parabolas, comes to some kind of point here. Okay, so it was very important to understand how to perform transformations in a 2D plane, And my claim is this leads up to something called the Jacobian, which you can think of as a U substitution for double and triple integrals. Okay, great. Thanks for watching.